Okay, so now we are in the new chapter section, chapter 14, section 4.1. We've done a lot of work up to this point to get to functions of several variables. So what we've been used to doing with basically two-dimensional stuff in the past is functions of two variables, usually like a y and an x. So we're going to be able to discuss functions of two or more variables verbally, numerically, algebraically, and visually or graphically. It's kind of the goal here. All right, so again, we're used to having something like y equals some function of x, y equals f of x of some kind, where we know that y is a function of x, or in other words, x is the independent variable and y is the dependent variable. For example, something very simple, if we just had y equals 2x plus 3. Okay, so the input here is x, or the output is y. So basically the idea is if we input x equals 2, you would get out 7 for y. Okay, that's kind of the way we've been doing things in two dimensions. Now what we're going to use is z is some function of both x and y. So now x and y are both inputs. They're the domain. They are going to be the independent variables, where z is the output or the range or the dependent variable. Okay, so again, it's just going to follow through now into a three-dimensional thing. So an example, something relatively simple, z equals x squared plus y squared. So once again, your input is going to be, let's do it like this, x and y. Remember, input is the same as your domain, which is also your independent variable. And then your output, which is the same as your range or your dependent variable, in this case is z. So if you were to say, you know, x is, I don't know, 2, y is 2, we'll keep it simple. Then z, 2 squared is 4, another 2 squared is 4, so we're going to get z equals 8. Okay, no big deal there. That's the basic idea. So we're going to input two variables and we're going to output a single variable. So a graphical representation of this. We just kind of sketch a three-dimensional space here. We're going to have some kind of a surface floating up here in space, whatever this thing looks like, you know. Who knows exactly what this thing's doing? It's just something floating up in space where, I don't know, maybe it looks something like this. And then over here, it does something like that. I mean, who knows exactly what this thing looks like? But you can kind of see how it's floating up there in space. So the idea is the domain of this thing is going to be something which is projected down into the xy plane. So the domain, whoops, don't want that to look like a solid line. Excuse me, might be projected down like this. So that's your projection down into the xy plane. So the domain is basically this rectangular region. Whoops, accidentally hit extend my page there. Basically, it's kind of like that rectangular region down in the xy plane, whereas some kind of input is going to be based upon x and y. So you're going to have some kind of an x input. Oops, it's supposed to be green. There we go. Some kind of an x input, some kind of a y input, and then that's going to project up and give you some kind of a z value. So your X and your Y values will project up and actually give you some kind of a Z value someplace on the surface. So that's just kind of a graphical representation. So again, all of this down here in the XY plane is your domain. So it's the projection from the blue surface down into the XY plane. That's the domain. All right, so let's look at a practical example. This is the wind chill chart information of multiple variables. This is called the new wind chill chart. I actually don't know when this was taken from, so there very well may be an even newer wind chill chart. But as of whenever this was created, it was the new one. All right, so what we've got is we've got a chart which has the wind in miles per hour across the top and the temperature in degrees Fahrenheit down the side. All right, so what that's saying is the wind chill is a function, so we'll call the wind chill W, it's a function of both the temperature and the velocity, the wind velocity. Which makes sense. If you think about it, if you went outside in, I don't know, and I'm not using the chart for this, but if you went outside in 50-degree weather and there's no wind chill, it's gonna feel like 50 degrees. If you go outside, however, in 50-degree weather and there's a really strong wind, it's going to feel colder than that. So that's what the wind chill is. So the wind chill depends upon two different things. It's going to depend upon the temperature and the wind velocity. So for example, if I just wanted to find the function of 3010, what that's telling me is I'm going to find the wind chill, or what it feels like outside, when the temperature is 30 and the velocity is 10. Well, let's take a look at that. When the temperature is 30, that's here, and the wind velocity, which is across the top, is 10, that's there. So if we match up that column, then what we get is a wind chill of 21 degrees Fahrenheit, I guess. That's what this is measured in. So if the actual temperature outside is 30 degrees and the wind chill is blowing at 10 miles per hour, it's going to feel like 21 degrees Fahrenheit. That should hopefully make sense. That really probably should not be that much of a problem. But now let's say we do it a different way. Let's say I want to find the function of t, 10. What does that mean? Well, t is variable. Okay, t is going to change. The 10, however, I am holding constant. Okay, I'm not letting the 10 part change. So what this is actually trying to find is, how does the wind chill change? How does the wind chill change if the velocity is held at 10 miles per hour? Okay, that's what f of t, 10 is actually wanting us to find. How does the wind chill change if the velocity is held constant at 10 miles per hour? So basically what you would be doing is you would be looking specifically at this column right here, and you would have to figure out specifically what the actual change is depending on where you're trying to find it. Okay, so that's one idea. What if I said I want to find f of 30, v? Okay, hopefully after the last one, this will make more sense. So now what's being held constant is the actual temperature outside. So now we're saying if the temperature is 30 degrees, the velocity of the wind can change. So what we're trying to find here is, how does the wind chill change? How does the wind chill change if the temperature is held at 30 degrees Fahrenheit. Okay, so hopefully that makes some kind of sense. That's mostly a notational thing. So let's kind of recap real quick here, and then we'll actually do one more thing at the bottom of the page here, because we're going to talk about the domain real quick. So for every ordered pair, let's do this in purple. For every ordered pair, XY, there can be only one output. Z. So that makes it a function. For every set of inputs, ordered pair X and Y, in this case it's not X and Y, it's T and V, but in general, for every ordered pair, there can be only one output. In other words, I can't plug in, let's just say, for example here, I can't plug in 30 and 10 and get 21 degrees, but also get 27 degrees. That doesn't make any sense. It can't give me two different outputs. It can only give me one output. Okay, again, that's just kind of the idea of a function. The inputs can only yield one output. All right, so let's quickly talk about the domain. By the way, that's the wind chill in degrees Fahrenheit. That's kind of the function that gets you all that stuff, if you were interested in that. Nothing we have to worry about. So what's the domain of this function? Well, according to our chart, and that's the biggest thing, we can only go by the chart here. It looks like the temperatures go from -45 up to 40. So we're going to say that based upon our chart, -45 degrees is less than or equal to T, which is less than or equal to 40. And then it looks like our wind chill goes from 5 to 60. So 5 is less than or equal to our wind chill, which we called V. I'm sorry, not the wind chill, the velocity, to 60. So if we're going to sketch that, literally just going to create ourselves a, let's see, a T versus V, T, V axis. All right, and again, this is just a really rough sketch, but we know that the temperatures go from -45, so we'll call that -45, up to 40, we'll call that 40, and then the velocities go from 5 to 60, so maybe that's 5 right there, pretty close to the x-axis, and then that's 60 or something. It's not really drawn to scale, but you get the idea. So our domain is anything in that box, basically. So I'm going to draw this, see if I can sketch this. It's supposed to be just above the axis there at 5, all the way up to 60, and across. Whoops, missed. So this is our domain. Everything in that vicinity. Okay, and that's it. That's a sketch of your domain. So really you just have to make sure either your domain is based upon the given information or make sure that it's realistic to the situation. All right, so let's take a look at a couple of examples. Find and sketch the domain for z equals 2 over x squared minus y squared. So we have a fraction. The numerator is not a problem. It's the denominator that always gives you a problem in the domain. So basically, the denominator can't be 0. So what we need to do is we need to state that, okay, x squared minus y squared can't be 0. So how are we going to figure that out? Well, let's add y squared to both sides. So we know that x squared can't equal y squared. And then if we take the square root of both sides, remember that you get a plus or minus on one side. So y can't equal plus or minus the square, plus or minus x. So if we look at the domain of that graphically, y equals positive x is that line, y equals negative x. Oh, that was just a horrible line. Let's try at least getting part of that out of there. That's better. Y equals negative x looks like that. So basically anything that's on that dotted line is out of the question. Everything else is in the domain. Kind of hard to do that. Let's see. Let's do a highlighter. So we're going to have to shade everything in here. And we're going to shade everything up here. Basically, everything except for the dotted line. There probably is an easier way to do this, but this is just what I thought of. Everything that's not that dotted line. There we go. Try and come up with an easier way for these future problems, but that's it. That's kind of a sketch of your domain. Okay, let's do another one. Go back to an actual writing utensil there. So we want to sketch the domain for z equals the square root of 9 minus x squared minus y squared. So what might be helpful is to put that in a form that we're slightly more familiar with. If we square both sides of that, we get z squared equals 9 minus x squared minus y squared. And then if we add the x squared and y squared to the left, x squared plus y squared plus z squared equals 9. So what you have there is a sphere. Remember that the domain is the projection of that sphere down into the xy plane. So what we're talking about, what we're talking about is a circle. Talking about a circle, it looks like the circle is going to have a radius, or the biggest possible radius would be 3. So let me see if I can cheat a little bit there too. Can I draw a circle? I can draw a circle. I like that. Oh, look at that. A nice circle. It's got a radius of 3. How about that? Okay. So the domain for this thing, well, let's see. It says z equals the square root of 9 minus x squared minus y squared. So if you remember, basically, whatever's underneath the square root can't be less than 0. So basically, we're going to take everything that's under the square root, 9, trying to write with that, 9 minus x squared minus y squared, and make it greater than or equal to 0 to find our domain. So if we add the x squared and y squared to the right, we get that 9 is greater than x squared plus y squared, or basically x squared plus y squared is less than or equal to 9, which means that it's everything within the circle. Can I do this? Let's see. Can I fill? Let's try it. Oh, look at that. Oh, it got rid of my lines, but whatever, good enough. That was pretty cool. Learning something new. So there's your domain. It's everything inside the circle. And again, that's because this thing right here is a square root. So everything underneath the square root has to be greater than or equal to 0. All right, just a couple more examples. I think we got 3 actually, and then we'll come back with a second video. Okay, so this time we've got a function of xy, x squared e to the 3xy. We want to find, first of all, f of 2, 0. That shouldn't be too difficult. The domain of f of xy, and then the range of f of xy. We hadn't done that one before. So let's first of all talk about f of 2, 0. That's the easy part. That just means plug in 2 for x, plug in 0 for y. If we do that, we are going to get 2 squared e to the 3 times 2 times 0. So 2 squared is 4. E to the 0 is 1, so you get 4. So we're done there. Let's talk about the domain. So the domain, well, In this case, there's no value that x can't be. So x, use a little notation maybe you haven't seen before, is an element of the real numbers. Basically, it just means x can be anything. So that sideways curvy looking e thing is an element of. And then y, well, again, y can be anything because y can be anything up in the exponent of e. So y is also an element of the real numbers. Okay, that r with the extra line through it is the real number symbol. You've probably seen that one before. So if we put both of those things together, since x and y can both be anything, the domain is the set of real numbers in 2 dimensions, or what we call r squared. So the way that is said, it's the set of all x, y. And that's a 2-dimensional thing. It's a 2-dimensional domain because it's got x and y. It's an ordered pair. It's 2-dimensional. So the range, however, is going to be a little bit different. So the range here is that f of x, y. So let's think about this. No matter what I plug in for x and y, well, no matter what I plug in for x, it's going to be x squared. So at the very smallest, it would be 0. And with an exponential e to something, exponentials cannot be negative. They can be very small, but they can't be negative. So in this case, the smallest value that we're going to be able to get out of this is 0. But the largest value is obviously infinite. It could get as large as we want it to be. So the range is going to go from 0 to infinity. And what you should notice is that is 1-dimensional. Okay, it's basically linear. Your z values, or in this case, your f of x, y, like we call it z a lot, can only be one value. It's 1-dimensional. All right. Okay, not really much else to do there. So number 4, let f of x, y equal square root of y minus x squared over 1 minus x squared. We just want to find the domain. Okay, so obviously we have multiple things. This is really the same kind of idea as anything else when you have domain issues. So we can't have negatives under square roots, and we can't divide by 0. So we've got a couple of different things to look at here. First one is that 1 minus x squared cannot equal 0. So we know that x squared cannot be 1, or x cannot be plus or minus 1. Okay, we've also got this numerator to deal with. Now remember, you can't take the square root of a negative, so that y minus x squared must be greater than or equal to 0, which means that y has to be greater than or equal to x squared. And if you just go with the equal part, y equals x squared is a parabola. So that's kind of going to help us with our 2-dimensional projection here. So let's see, we know that x can't be positive or negative 1. So I'm just going to draw vertical asymptotes, positive and negative 1, because I know that that cannot be included. And then we've got y equals x squared. Let's go with purple, which looks something like this. Now it does have, that's horrible, I went below the line. It does have the equal to symbol. So basically, if I do this correctly, and y has to be greater than that, so it's going to be everything above that parabola. I think I'm going to have to go back to the highlighter here. I can't really fill this one. It's going to be everything. That's bad. I'm trying not to hit the dotted line here. I'm not doing a very good job. There we go. It's going to be everything above the parabola that doesn't touch the dotted line. So all of this, everything above the parabola that does not touch the dotted line. Obviously, it goes on infinitely in the positive direction. There's just not an easy way to do that, to show that, but it keeps on going forever. So that's your domain of number 4. One more and we'll be done with this one. So we want to find the domain of, in this case, f of x, y, z. So now we actually have 3 independent variables, and a fourth variable. So that means that the domain is actually going to be three-dimensional. Well, if we were to think about what we've got there, remember what's underneath the square root can't be negative. So 1 minus x squared minus y squared minus z squared must be bigger than or equal to 0. If I add all the stuff over to the other side except for the 1, I get x squared plus y squared plus z squared on the right, which is less than or equal to 1. And that, of course, is a sphere with a radius of 1. So what that tells me is that my domain is everything inside of a sphere of radius 1. So it's going to look something like this, and then something like this. There's your sphere. I don't know if I can fill it. I'll have to try. Can I do that? Oh, I can. It just doesn't look very good. So let's get rid of that. I wonder if just doing the highlighter is going to be better. Let's see. Highlighter. Can I just kind of color in? Oh, I can, and it keeps the dotted stuff there. Much, much better. All right. Everything within the sphere. So there you go. All right, that is way too long for this video. We'll come back with one more video, and we'll look at some contour maps and graphs and domain and range of those.